Hello, I'm Jonathan Aldrich, and today let's talk about generating a finite automaton. When we have a specification for the language, that specification might be expressed in terms of regular expressions for the tokens in the language. So we'll start by writing regular expressions for each language construct, except keywords generally will be a special case of identifiers. And then, to work towards a DFA, we'll first construct a non-deterministic finite automaton for regular expressions. Now, a non-deterministic finite automaton might have several transitions out on a character. And so we'll next convert that non-deterministic finite automaton into a deterministic one, using a set of subsets construction that I'll describe in a few slides. We then minimize that deterministic finite automaton to find equivalence classes and make it smaller. And then we'll fix up the result with various details like implementing the longest possible token rule, discarding white space in comments, distinguishing keywords from identifiers, saving the text and the token location, and returning a special end-of-file token at the end of the file. So let's start with the construction that goes from regular expressions to non-deterministic finite automatons. The base case is that we're reading a single character from the input. Call it character C. So what we're going to do is we're going to generate a non-deterministic finite automaton where we have a transition from a start state with the character C to a final state, which I'll denote by a state with double circles. Okay, so that base case is shown here at the top of the screen. Now, using a regular expression, once we have a regular expression, we can construct bigger regular expressions by combining them in various ways. So let's imagine that I have a regular expression for something called A, and then I have a different regular expression, B. If I want to concatenate these, then what I'll do is I'll simply unify the output of A with the input of B. So we have a start state, which was the old start state for A. We have all of the A construction here. We have the middle state, and then we go through B to the final state of B. If we want to do alternation, and again, we have two starting states, two starting regular expression, non-deterministic finite automata A and B, we can combine them by having a start state with an epsilon transition that can either go to A or B, and then at the end, the final states of A and B have an epsilon transition going to a new final state for the composed non-deterministic finite automaton, right? So here you can see where we're using the non-determinism. Basically, whenever we have a choice between A and B, we'll use an epsilon transition, and epsilon is reading nothing from the input, and so we just non-deterministically go either to the A or the B. We recognize the A or the B, and at the end, we go back to a final state. And here we use epsilon not because it's non-deterministic, but just because we're not adding anything to go to this final state. A critical part of this representation is that the start state and the final state are always kind of independent of the other states, and that's what allows us to naturally compose these NFAs together. Finally, let's look at how to do the Kleene star, right? That's our other fundamental regular expression construct. Here we have some regular expression A, and we want to produce A star. How do we do that? Well, we have a start state. There's an epsilon transition all the way to the end state, which is what happens if we don't do any A's at all, right? But if we have one or more A's, then we'll do an epsilon transition to the beginning of A. We'll read A, and then we have, again, two epsilon transitions. One, when we're done, we go to the final state, or if we're going to continue and read another A, we have an epsilon transition to go back and read A again. So with these four basic techniques, we can construct a regular expression, a non-deterministic finite automata for any regular expression. Let's go to the whiteboard for an example. All right, let's apply our construction of a non-deterministic finite automaton from a regular expression using our digit example. So d star dot D or D dot D star. Okay, we're going to start with the very simplest notion. So for a dot transition, we'll have the start state, and on a dot, we'll go to the final state. Similarly, when we get a D, we'll transition from start to final state. And now we have non-deterministic finite automaton for dot and for D. Given that, we can compose them. So we need a dot D and a D dot. And so we can put these together, right? Dot D will just be dot D, and then that's final. And of course, we have another one, right, where we have D dot. So that will have a start state, followed by a D, followed by a dot, and then we have a final state. Now we need an alternation between these two states, right? So we'll have a start state and two epsilon transitions. And then on the top, we'll paste in this, right? So we'll have dot D and then go to a final transition, a final state, and then we can alternately have first the D and then a dot, and then go to our final state. Finally, we want to put together, yes, and then we need a D star, right? So the D star will start with this one, right? And we'll add a we'll have a start state, right? And then we go to the inner part. We have an epsilon transition to the inner part, which is just a D. And then we have an epsilon here, and an epsilon to the end, which is the final state. And of course, we can skip the whole thing with another epsilon transition. So to finish everything, now we're just going to hook up a D star at the beginning to this dot D or D dot construction in the middle, and then another D star at the end. So we'll get the start state, epsilon to D, another epsilon, a way to skip, and a way to repeat. Here we'll have the part from the middle, so I just bring this down here. Epsilon, epsilon, dot D, or we can have a D followed by a dot, and these are epsilons. And then we put another D star at the end, right? So epsilon 2 in the middle, we've got one D, we've got an epsilon that allows us to repeat that D 0 or more times, we got an epsilon to go out, we have an epsilon to skip the whole D star at the end, and then this is our final state. All right, so non-deterministic finite automata can be used to recognize regular expressions, and now we know how to produce them from regular expressions. But unfortunately, they're inefficient at doing that. And the problem is that the implementation has to track many paths from the NFA to find out which one of those is actually feasible, right? Every time we go two different directions, we essentially have to explore both of them to find all the possible ways that a token could be recognized. So we would like something more efficient, and we can in fact extract a more efficient deterministic finite automaton from the non-deterministic finite automaton. And the deterministic finite automaton is going to be better because no matter what token we get, we always know the next state that we need to go to. So each state in the deterministic finite automaton in our construction will be a set of NFA states. So this is called a set of subsets construction. The start state of the NFA contains the start NFA state, plus all the states reachable through epsilon transitions, right? So basically we're going to collect all the places you can get without reading any characters in the NFA, and all those states together will be the start state of the DFA. And then for each input that can be consumed from one of those NFA states, we create another DFA state from the set of destination states. So let's look at that construction on the whiteboard. Okay, next, we now have a non-deterministic finite automaton. We're going to turn that into a deterministic finite automaton with the set of subsets construction. So the first thing I'm going to do is number every one of these states in the NFA. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay? Now you may recall that the first state in the deterministic finite automaton is going to be the subset of states that include the initial state, but also states reachable through epsilon transitions. In other words, states we can reach in the non-deterministic finite automaton without reading any characters, right? So that will be the new start state of the deterministic finite automaton. So we're going to go, and we're going to call this state A. And I want to track which states from the original NFA are part of that DFA state, okay? So clearly, the first state, the initial state of our NFA, is in the states of A, right? So it'll include 1. But we can go with an epsilon transition to 2. Okay. Now after 2, we have to read a D. So we don't go any further there. But we can also go from 1 all the way over to 4. Okay. So we have 1, 2, and 4. Let's see if we can go any further. From 4, we can go to 5 or 6. No, sorry, 5 or 8, right? And then after that, we have to read either a dot or a D. So we have 1, 2, 4, 5, 8. So A in the deterministic finite automaton is a state that represents a subset of states from the original NFA. Okay, now let's look at what happens if we are in one of these states and we read a D. Okay, so now if we're in state 1, we can't read a D, so we don't have to worry about that. But let's look at each of these states from the original NFA. We see that from 2, we can get to state 3. Okay, so I'm going to draw a transition from A to some state B here, where we read a D, and state B will include a 3 from the original NFA. Okay? Now, what else can we do? Where else can we read a D? Well, we can also read a D from state 8, right? The other ones, 1, 2, 4, 5, we can't read a D, right? Only 2 and 8. So 8 will bring us into state 9. So we have 3 and 9 here. But notice that if we're in 3, we now have some state transitions, right? An epsilon transition to 4, 5, or 8. So we also have 4, 5, 8 here. And from 9, we can't do any epsilon transitions, so that's all, right? So B, if we put these in order, it's 3, 4, 5, 8, and 9. Now we want to complete the picture for D, for B, and for A, right? So what else can we do if we're in state A? Well, state 5 can have a dot, right? So we can have a dot here, and that'll go to a state C, which has 6 in it. And 6, when we're in 6, we have to read something, so that'll be the only NFA state in the new DFA state. If we're in B, well, B includes 8, where we can read a D, okay? So, and 8 will go over to 9, so that stays here, right? So if we read a D, we go from 8 to 9, but they're both part of D, both part of B, so we'll stay there. And then from B, if we're in state 5, we can also read a dot and go to state 6, right? So there'll be a state D here, which goes to 6. If we were in state 9, then we've also gone to 10, right? So this will be 6 and 10, and then from 10 there's some epsilon transitions, right? 10 to 11 to 12 and 14. 10, 11, 12, 14. All right, so on the whiteboard, we grouped the first 2 states, A and B, which represent the subset of states. So A represents the states 1, 2, 4, 5, and 8 from the non-deterministic finite automaton. B represents the states 2, 3, 4, 5, 8, 9 from the non-deterministic automaton. And if we follow the same approach, we can also get states C, D, E, F, and G, which represent all of the states as shown here in this diagram. Now we have a non-deterministic finite automaton, but it turns out it's a little bit big, right? There are some unnecessary states here. If you kind of look at D and F and G, we're just having a transition on a D from each one of those to the next. And they're all final states, so why do we even need to do this, right? So we can minimize this DFA to produce a smaller and more efficient one, and that'll be our next step. So DFA minimization, we're going to start by merging all the DFA states into 2 equivalence classes, final and non-final. And then iteratively, we'll identify non-deterministic transitions from these states, because we basically glommed them together and we've reintroduced non-determinism. But we can easily get rid of that non-determinism by basically splitting states to avoid it. So let's look at an example here. Consider the diagram on the left, right? So from this big state chart, this big state diagram, we've started by merging all the states that are non-final together, A, B, and C, and then we've merged all the final states, D, E, F, and G. And so here we have A, B, C, D, E, F, G. The problem is that there are non-deterministic transitions from the first state to the second, right? So from ABC, if we get a D or a period, then we could either stay in ABC or we can move to D, E, F, G. So it turns out we can make the D transition deterministic by splitting it into a state that represents AB and a state representing C. And if we look at the original diagram, we can see why, right? So the D transition, if we merge A and B, then D stays within A and B, right? Because we go from A to B and then we stay within B here. And then if we're in C, the D transition moves us to D, E, F, G, right? So we can split ABC into AB on the one hand and C on the other hand, and then we'll make this transition deterministic. We can also in the same way choose dot as the thing to make deterministic, and that will result in a different split, right? We'll split into AC and B. But we need to pick one of these. And so we're just going to arbitrarily pick the first one, right? It doesn't matter. They'll both work. But we'll take the first, split ABC into A, B, and C, and proceed. So here's what we started with. We then move over here to the case state where we have A, B, and C. And you notice that now the D transition from AB always stays within AB, and then the D transition from C always goes over here. So we've gotten rid of some of the non-determinism, but we still have the non-determinism in the dot transition. So in this case, we can split AB into A and B, and then the D transition moves from A to B. That's just from the old diagram. And then from A, we move to C on dot, and B, we move to D, E, F, G on dot. And so now we have a deterministic finite automaton, but it's much smaller than the one we had before. Let's check our understanding.